So in this activity, 1.11, we are interested in finding the derivative of several functions. So the first one, f of x equals 1. Well, we could use the limit definition, but let's just think about what's going on. We have a function that's constant, so its graph would look like a line at y equals 1. Notice it's neither increasing nor decreasing, so it's got a constant rate of change of 0. So, without even using the limit definition, f prime of x is going to be 0 everywhere, because everywhere it's got a slope of 0. B, g of t equals t. Notice what we have now. We have a linear function, and what's its slope? It's got a slope of 1. So we can say, without applying the limit definition, g prime of t equals 1. Because it's the slope of the linear function. It's a constant slope. It's the same everywhere. Now we're going to start applying our limit definition to get some practice with that. So part C, p of z equals z squared. So, applying the limit definition, we get p prime of z equals, now we're going to take the limit as h goes to 0, and now we're going to do z plus h, the quantity squared. That's that second point, minus z squared, that's that first point, change in y, all over h. The rest, now that we have it set up properly, is algebra. So we get the limit as h goes to 0. Most common mistake in this, z plus h, is z squared, is not z squared plus h squared. It has to be FOILed out. So you get z squared plus 2zh plus h squared minus z squared all over h, which is equal to the limit as h goes to 0. Notice what happens. The z squareds are going to cancel. That's good for us because both terms in top have an h left in them. So we have 2zh plus h squared all over h. I can factor an h out on top. Limit as h goes to 0 of h times 2z plus h all over h, which allows those h's to cancel. Now I can solve the limit by direct substitution, plugging in 0 for h. I get left with 2z, and there's my derivative. So the main part is setting up the difference quotient and then applying algebra. So let's take a look at D. We have a cubic. Q of s equals s cubed. So again, first step, set up my difference quotient. And notice I'm calling it q prime of s because it's not q of s, it's something a little different. So now I'm going to have, oops, we almost forgot our limit. That's what makes it a derivative. Otherwise it's just a difference quotient and it's just an average rate of change. So we're taking the limit as h goes to 0 of s plus h cubed minus s cubed all over h. Now again, we're going to apply some algebra. S plus h, the quantity cubed, that needs to be multiplied out. That's s plus h times s plus h times s plus h. Now for the purpose of this video, I'm going to give the multiplied out version. So s cubed plus 3s squared h plus 3s h squared plus h cubed. Now you should go ahead and verify that because you need to know how to multiply this out, then minus s cubed all over h. But again, for the purposes of this video, to save a little time, this is the multiplied out version. The s cubes once again cancel. Every term left has an h in it. So like I did before, I'm going to factor out the h. Limit as h goes to 0. H times 3s squared, so that's that term, And h factored out of here is plus 3sh plus h squared all over h. Again, we get those h's to cancel. I can do direct substitution. 0 for h, that's going to make that 0, that's going to make that 0, and I get left with a derivative of 3s squared. And you're probably noticing a pattern. The derivative of z squared was 2z. The derivative of s cubed was 3s squared. We're going to explore that in later sections.